Oh, thank you for coming. And can you see me? Can you hear me in SDSU?
We can hear
Okay. Okay. So we are continuing the third chapter of our course, the density functional theory. And let me briefly go through what we are doing, go through all types of our activity, and then we will concentrate on scientific part. So here you can look on the book that I was reading last night, and here are two most interesting pages. And if you are in SDSU, you can find same pages on the D2L.
Sure.
I have copied it. So we will start doing the essence of density functional theory today, and maybe next 4 or 5 lectures. Last time we did agree to extend the homework 6, and it is due Friday night. So probably we are not going to extend it more. So if there are some difficulties, let me know today, not tomorrow.
Okay.
And the number 7 will be much easier. So I admit that number 6 was really hard and a lot of labor. The rest of homeworks should be maybe 3 times easier. Well, we are going to meet in the computer lab in the basement of Arts and Science on coming Tuesday, and we will discuss how to analyze the output of the WASP software. In about 3 weeks from now, I would like to offer you to make presentations about sharing the practical skills about how to use the software, and it is the skills that you are going to accumulate during this several weeks. So until the beginning of the April, we set up a goal to understand principles behind the density functional theory. Last time we have entertained ourselves by looking how multi-electron wave function and multi-electron operators can lead to observable through much simpler concept of one electron orbitals. And we also touched the Hookeman theorem and the first step towards solid state. So today we will briefly review what was done in the lab, so that if by some reason you were not able to attend, you have an idea what was there. And then we should set up approximate plan for 5 next lectures, how to establish a pace, how to accumulate the information about density functional theory. And today we still are not taking the actual density functional theory. We will be touching the foundation, some very simple background theory that was developed 40 years before appearance of actual DFT. Looking onto this Tomasa-Fermi theory, you get a confidence and understanding basic concepts that help in being fluent in density functional theory. Okay, so it was a review of the lab. So we were trying to do our first steps in WASP software, and this software is designed to describe periodic solids. Oh, it is not. talking. The periodic solids, and therefore the software has some specific. It is a little bit different from most of quantum chemical software, which is designed to describe small molecules. So we were trying to practically acquire hands-on experience on what is unit cell, what is translation vector, and why, what it is, and why we need to add vacuum layer. So we were building the input files for the software for one of the models that we have developed in our previous webs. So we took whatever we had before and just converted it in a smart way for new software. And the good news are that if you have missed last lab, but you do have X-ray crystallographic data in the format of .cif file, you still are able to generate healthy input files for the VASP software. So yes. Is it better? I can keep it as a standard microphone. Does it help this way? Okay. Any better? Okay, can we put regular mic just? Is it better this way? Okay. So let me show some pictures that we were drawing during the lab. So it is one of the models that we developed before, the minimalistic possible nanowire of titanium dioxide. And we were establishing the understanding of the concept of what is the minimal repeating unit that repeats again and again, and how to establish an additional layer of empty space between those periodic units in a practical sense. And the protocol of this lab is on the D2L. The important point that empty space should be added in all three directions in order that those models do not interact with each other. So even if it established as periodic in, let's say, Z direction, one needs to add some vacuum layer in X and Y directions. So it is a very brief summary of what we were doing for like 2.5 hours. So what is the roadmap? How can we quickly and efficiently learn what is DFT and how to use it? So there are some definitions. There are some background theories which are not actually DFT, but they're really helping. And it is what we will be doing today. Then there is a theorem, several theorems that prove that this magic and very simple theory can help and solve complicated problems. And then there are practical implementations, the algorithm for making DFT computation. And there are procedures to compute observables. So it will add up into about 6 meetings or 5 meetings. So we are going to focus on background theory, and it is it was developed maybe 40 years before, or even 50 years before any computation were made possible. And in 20s, it was developed right after the development of quantum mechanics, and it holds the name of Thomas and Fermi. So this theory was used only as a toy, as a model that was never believed to help in describing real molecules and real materials, but there were some basic concepts that later were found very helpful. So in this theory, in this model, one considers the infinite space, vacuum, filled by many electrons. So there are no ions, or maybe in next development of the theory, one can assume that all ions are distributed as a homogeneous background positive charge. But there are no point charges, there are no attraction centers, so the whole space is considered as being filled with electrons that do not interact. So it is already a very strong approximation. And therefore, this model is often referred as electron gas model. So the major goal of DFT is to replace multi-electron wave function by something simpler. Instead of wave function, one tries to use charge density. And since the major goal of considering electronic part of a molecule, electronic diagonalizing, solving for electronic part of the molecular Hamiltonian, one is looking to find the total energy, total electronic energy. And before with Hartree-Fock theory and with many other theories, one is finding the total energy based on wave function, using the concept of expectation values. Instead, there is a untrivial, but actually computationally very simple and efficient way to compute total energy based on the distribution of charge. So distribution of charge is much simpler concept, because it has less degrees of freedom. So wave function depends on positions of all electrons, and charge density depends only on one coordinate. So it is really function of one variable or three variables if we are in a three-dimensional space. So there are some assumptions, derivations behind it, but this is a function of one variable. And therefore, it is immediately expected that it will be much quicker, much more efficient computationally. But it took several years for developers of this theory to prove it to the community. So many people were not believing that one can avoid wave functions and expectation value concepts. Yes? Uh-huh. No, no. It is wave function is defined as multidimensional object depending on position of each electron in the system. Charge density just tells us in average how many electrons are located in a small volume. And it sounds much simpler and very surprising that this information is enough to find the total energy. Okay. So I will try to deliver this Thomas-Fermi theory of electron gas, which is a fundamental background for density functional theory. And there will be several technical details which are not of critical importance. So if you are busy, if you are thinking about something else, do not worry. So focus only on what I will be telling at the beginning and at the end. So the intermediate steps are just for continuous narration and in case some of you want to dive into theoretical derivations later. So what we will be doing is to check before any proofs, before making formal definitions, we are taking the simplest possible example and we are trying to find a connection between total energy of many electron system and amount of electrons in a selected small volume. This sounds really crazy. So there are no expectation values. There are no operators. There is some different ideology. So there are several steps on this road, and this is very oversimplified theory because there are no ions, there are no attractions, and interaction between electrons is also neglected. The only thing that we keep is that electrons obey Pauli principle and Fermi distribution. Okay, so we are looking on the universe that has only electrons, nothing else, vacuum and electron. Then we split this universe on many cubical boxes. And then we focus our attention only on one box for maybe half an hour, and then we will return back to the whole universe. Split universe on boxes. And fill it with electrons. So in case we want to make it rigorous, we need to define what is the size of the box, and let it be square, so with size L, L, L. And we are going to, so the volume of a box is L cubed. The amount of electrons is delta n, just notation per cell. And we are going to find the energy of all electrons in one cell. All electrons in one cell. And then we are going to find total energy by making summation over all cells. And at the end, we are going to see that this total energy will depend on the ratio of the amount of electrons per cell divided by volume of one cell, which is density of electrons. So we are going to establish connection between density of electrons per unit volume and the total energy of this electronic system. Okay. Our electrons are quantized. We do not neglect quantum mechanics. We believe that if there is a particle in the box, it takes not any possible states, but only those that that follow the quantization rules. So only specific energies, specific values of energies are allowed that follow the specific values of quantum numbers, which are integers. So this formula follows from the kinetic energy in a free space, momentum squared over mass. And in one dimension, also the quantum number gets squared, so the spacing of levels becomes sparser and sparser in one dimension. In case we do have a three-dimensional universe, or three-dimensional box right now, then the energy of one electronic state is determined by three quantum numbers, the quantization number in X, Y, and Z. And this is just extension of particle in the box concept onto 3 dimensions. Okay? So these 3 numbers squared recall the equation of a sphere, right? So if you have 3 distances squared and make it equal to some constant, it will correspond to a sphere. And same way, in the space of quantum numbers, we can establish a sphere. There is a sphere in space of quantum numbers. And we do want to find the energy of all electrons in this box. So we probably want to populate all the states with as many electrons as we do have at our disposal. So we need to know either how many electrons we have in our universe, or we can use some average quantity that describes the number of electrons. chemical potential of Fermi energy. We're going to introduce it. So we are going to make a summation over all available states, and we are going to simplify it so that we can forget about directions and speak only about amount of states per given energy. So instead of this 3 quantization numbers, we are only interested in number of states that do have the same energy. And since it is a sphere in the space of quantum numbers, there are degenerate states. So any state on the sphere will have the same energy. And for different radius of the sphere, number of the states will be different. There will be different degeneracy. So we can ask a question: what will be the number of states on the surface of the sphere? So the states that do have energies in a very narrow range. And we also may want to ask ourselves what is the number of states that have energy less than some threshold. So there is nothing new now. It is what we were doing in physical chemistry class when we were trying to acquire the concept of density of states. 1 dimension, 2 dimension, and 3 dimension. Okay, so this is our quantum numbers. And each point on this diagram corresponds to state in this box that can be occupied or not occupied by an electron. So remember, we were writing that energy is determined by an x and y and z, and it means that for each 3 numbers there is a state, right? And if we specify these numbers, we can just plot them on the diagram as x's. And for simplification, I'm drawing 2-dimensional, but same with a little bit more artistic skills can be drawn in 3-dimensional. So we have a sphere, and we are interested in 2 things: the amount of these dots that satisfy the condition that an x squared and y squared and z squared is less than some r squared, some given r squared, so what is in this area. And our second interest is what is the amount of degenerate states that fall in the range between r and r plus delta r, right? And in order to answer this question, one uses the middle school or high school math for area of a circle or volume of inside the sphere, right? So if we need this blue area, and if we are thinking about a 3-dimensional situation, it will be 4 over 3 r to the power 3, right? So it will correspond to amount of states inside this area. And if we need the amount of states inside this degenerate state inside this area, we just take derivative of this one. This or phi, this d phi will be, we take derivative of this. 3 comes to the front, r squared dr. So we are trying to establish a counting for number of states, because later we will need to compute the total energy inside one box, and we are going to put electrons in each of the states and then add it together. So in order to find total energy, we need to know the value of energy and the degeneracy of a state. Okay? Here I was doing same drawing at home, but we are done with this. So our energy and this pseudo radius are connected to each other. So if you know this R capital, we also know the energy of each of the states, and we can write this radius as function of energy. Will be, since here it is R squared, which comes from x squared plus y squared and z squared. Then if we want to express this radius as function of energy, it will be square root. Okay? And then this equation for total number of available states inside the sphere can be cast, can be expressed in terms of the threshold energy. So we know that for energy value epsilon, there are this much states that are having same energy or less than this one. Okay. And then if you know the amount of states inside the sphere, we also can determine the amount of states on the shell of the sphere, right? But what is important that we need to find the amount of states on the shell of the sphere as a function of energy. So we are taking this this number of states as function of energy and just take a derivative. And we see that, well, it looks not very impressive and not very important, but later one can draw important results, important conclusions out of it. So this one is amount of states on this tiny shell. Amount of states that have energy epsilon, or maybe a little bit more, a little bit less than energy. Amount of states with energy between two narrow ranges. And actually, this thing is equivalent to density of states that we were already plotting in some of our exercises. So it is applied to different objects. We were plotting it for something that can be probably made as a result of synthesis. Here it is abstract model, but it is amount of states per interval of energies. Per interval of energies. And if you see that it is in power 1/2, it means the square root of epsilon, and we see that it increases, but with smaller and smaller rate. Okay. So we do have set of states in this one box, and we want to populate them with electrons. So we do not know exact number of electrons. We are not going to specify it right now. We are going to borrow, to import the concept of Fermi distribution that is always correct for electrons, for fermions, which tells that for given energy, one can that there is a very strict, very definite answer of whether a state is occupied or not by an electron if one knows the energy. So occupation of a state is a function of energy. And it corresponds to this Aufbau principle, that states with lower energies are populated and states above some threshold are not populated. So this idea is summarized in Fermi distribution formula. And here is this equation, and it uses the value of this threshold energy. And it also uses the temperature. But the formula will be valid in zero temperature too, even if our abstract universe is very cold. So if you take this fragment of the formula and draw it as a function, we see that it increases. So as far as we go above Fermi energy, it increases stronger and stronger, and if we go below Fermi energy, it approaches 1. And if we divide, if you put this function into denominator, then in limit minus infinity, 1 divided by 1 will be 1, right? And in the limit plus infinity, 1 divided by something big will be 0. So this formula is designed to represent occupation of a state by an electron as a function of energy. So for those states that have energy less than Fermi energies, they are occupied, 1. For those states that are above Fermi energies, they are unoccupied. Occupation is 0. And now we are going to merge these two things together. So we have list of all states. We know the degeneracy of each state, and we know whether a given state is occupied or unoccupied. So our input here is only the size of the box that determines the spacing, and this Fermi energy, which is something that can be measured for real systems. And here it is a parameter of the model. So we are looking for total energy. So we are making a summation, or if it is continuous integration of value of energy then occupation, whether these energy states are occupied or not, occupation, and then the degeneracy, the thing that we were describing with these spheres. Not amount. Let us say degeneracy. Degeneracy. Okay. So let's consider the zero temperature limit when this Fermi distribution is strictly 0 or 1. Temperature goes to 0. Then instead of putting this distribution function into the equation for total energy, we can just stop integrating after we reach the threshold. Stop integration after reaching the threshold. So we remove the f function from this expression, right? Only energy and degeneracy, but we set up specific limits from 0 to Fermi energy. And Fermi energy is the same as chemical potential. So there are some constants that we are not, we do not care right now, and the degeneracy is proportional to square root of energy. So we take energy times square root of energy and integrate it. And, so the total power here will be epsilon to the power 3/2. And during the integration, the power of polynomials raises by 1, right? And one gets that total energy is, and then we use the specific limits. So on the lower limit it will be 0, at upper limit it will be Fermi energy into the power 5/2. So we are not done yet. By now we do have the energy of all electrons in the small box as function of this parameter of Fermi energy. But we do want to express this total energy as function of density of electrons. And the trick is that on one hand we express total energy as function of Fermi energy. On another hand, we will express density of electrons as function of Fermi energy. So there will be two things depending on the same parameter. And then we will combine them together and inverse the dependence. And finally, so we have three components: energy, total energy, Fermi energy, and density. And then we will exclude Fermi energy from these three things, and we will connect total energy and density of electrons. So we are halfway through this tactical goal. We do have energy as function of Fermi energy. Now we need the second half. We need the density of electrons as function of Fermi energy. Okay? Make sense? So density is a number of electrons per unit volume. And let's find the number of electrons in this unit volume first. Number electrons in a box as function of Fermi energy. Okay, so we are going to use almost the same thing as we did on the previous slide. The only difference that we do not have energy here. So we just multiply degeneracy times the occupation. So if a state is occupied by an electron, we count it. If it is an empty, we do not count it, right? Therefore, we do we remove this function and just keep integrating until we reach this threshold, until we reach the chemical potential, until we reach the Fermi energy. So we take the degeneracy function and we integrate in the specific limits. So this degeneracy function is some constant times square root of energy, and here we just integrate this the square root of energy. by integration of polynomial, the power raises by 1, and we take it at specific limits from 0 to the threshold, to Fermi energy. So we see that total number of electrons per volume is some constant times Fermi energy to the power 3 over 2. So it is what we were looking for. We have two components. Two components. Total energy per cell or per box.
Right.
And we have number of electrons per box. And they both are defined as function of Fermi energy. So what if we take this function and invert it? So we can express Fermi energy as function of number of electrons. It is just a toy mathematical operation. We do not put any science behind it. So if we delta n is e to the power 3 over 2, then epsilon will be equal to the delta n to the power 2 over 3. Okay, and now we can take this Fermi energy and plug it into expression for the total energy per box, right? This one depends on number of electrons. And we plug this expression for Fermi energy into expression for energy per box. And then we combine these two powers. This 2/3 comes from our number part, and this 5 over 2 comes from the energy side. And when we combine them together, we get that energy per box depends on the number of electrons per box. Yes?
Constant is multiply of previous one plus times new one, right? Because we have two constant already, right?
Well, the constants here are different. Like first constant, second constant, and here will be the third one.
Yep.
Just skipping, it will take extra 15 minutes to meticulously go through all the things, but it will not change the conclusions.
Right, but I noticed the same size of
Yes,
font.
yes, they're different constant. Thank you for pointing out. So we have a connection between energy and number of electrons, but we do want density. So density of number of electrons per volume, right? So we just won't have a change number to density. Then we anywhere where we have delta n, we can divide it by volume and multiply it by volume. And then keep this volume since it is as a constant, and then rename this as a density. And what is interesting and important for projection of this theory to the rest of DFT, that this density doesn't need to be the same in different boxes. So in one box it can be one density, in another box it can be another density. Therefore, one puts that it depends on the position. So we put this cube of the side of the box in the denominator here, and put it in the numerator here, and play with powers so that we just redefine the constant. And then we see that the energy per box depends on the density of electrons, number of electrons per unit volume, in some very simple form, so some power dependence. So it's really crazy. So we just know how many electrons are here and there, and we compute the total energy. It is very fruitful. If it is possible to work for any molecule and any solid, it makes possible to compute almost any system of any size. Later we will see that there are some limitations, but it is a big leap forward. Well, there is a little addition to this. This one is defined in a specific position. If you want to go forward, you need to integrate it over the whole space. Three-dimensional space, and this will be true total energy. So this integration is a procedure of establishing correspondence between a function here our function is rho and a number. And here our number is total energy. So in typical in first steps of calculus, one operates with functions when there is a correspondence between one number and another number. Here we establish a correspondence between function and a number, and it is a little bit different. Question? Well, in the limit of smaller volumes, one replaces summation by integration. You can say this epsilon total summation over all boxes constant times density 5/3, and we can write in each box. Okay, so we establish correspondence between a function and a number, and rigorously such type of correspondence is referred to different word as a functional. And in notation, one uses the rectangular brackets instead of round brackets. So out of the rho as function of position, density as function of position, one gets a single number, energy. And this is an example of functional. Now. So we cannot say that we know density functional theory and we can sit down and write a code. This is the simplest example. Here we didn't model the ions. So it is a very strange universe without actual atoms and molecules. We didn't took into account correlation, exchange, and any type of Coulomb interaction between those electrons. We just taken into account the concept of one electron per one state. But we did show, actually not we, Thomas and Fermi, showed that it is possible to characterize total energy of the system based only on density of electrons per unit volume. And we are going to work out this concept and apply it to real molecules and chunks of solid materials, maybe some nanostructures, to see if it will be more efficient or more helpful than Hartree-Fock theory that we used before. So with this, I would like to announce end of the lecture. If there are any questions, I'm happy to answer.
Dr. Kilin.
Yes.
What is the in the homework there was LDA and there was mention of DFT. What is the relation?
Once again, I think I understand what you're asking, but please repeat your question.
I was just trying to ask you about the homework, and there was a mention of to do the homework using LDA.
Okay. So we are going to switch from Gaussian software to WASP software, but as a final accord, as a final application of the Gaussian software, we would like to use it for density for one example of the density functional calculation. So LDA is is the simplest functional. LDA is an example, one of the examples of DFT. Example of DFT. So this abbreviation LDA is very popular in physics community and a little bit less popular in chemistry. It stands for local density approximation. And it relates strongly to what we were doing today. So we did establish connection between total energy and the density of electrons only in one space. So in most of other dependencies, in most of other connections, most of other functionals that do connect density to the energy, one goes beyond this and uses in addition uses, for example, derivative of density. And if one uses derivative, one says that derivative or gradient. So there one integrates not only over the density but also over some function of a gradient. And then it is a several GGA functionals. And LDA means that it is the simplest possible functional where energy depends only on this distribution in a simplest, in a most direct way. And it doesn't include any products of density or powers, any derivatives of density or some other admixtures. So the LDA is the simplest working form of density functional theory. And it is implemented in most of the codes, including Gaussian. Does that answer your question?
Yes.
Okay. Anything else? Other questions? If no, then thank you for coming, and meeting is dismissed.
Oh, yeah.